Good day once again, class. So for this presentation, we are going to convert a base 8, which is an octal, or base 16, sometimes we call this the hexadecimal number system, into base 2, which is the binary system. So there will be some rules that we have to follow whether or not we are going to convert the octal base to a binary base or a hexadecimal base to a binary base. So this technique class that I'm going to present to you is also reversible. In other words, if you're going to convert base 2 to base 8 or base 2 to base 16, we can also convert back base 8 or base 16 back to base 2. And of course, we can use the following rules to follow. So these are actually considered as a sort of a shortcut that we use in converting base 8 or base 16 back to base 2. So when we are going to convert base 8 into base 2, we rewrite the digits in base 8 as a sum using 4, 2, and 1 as a combination. Remember that base 8 has only digits 0, 1, 2, 3, 4, 5, 6, and 7. And if you're going to combine any of these three numbers by adding, like 4 plus 2 is 6, 4 plus 2 plus 1 is 7, 2 plus 1 is 3. Then, of course, if 4, 2, and 1 are not present, then definitely we have zeros. And once we convert them into 4, 2, and 1, then we put 1 as a multiplier to any of these digits, okay, that is present. Otherwise, we put 0 as a multiplier. Then the corresponding binary digits are the combinations of your ones and zeros that found besides its digit 4, 2, and 1. So for us now to understand this given uh, rules, so we have here an example. So if you're going to express 63 base 8 into binary digits, so remember that your binary digits are only in a form of 1 and zeros. So first thing is that we are going to rewrite each digit, the 63, as a sum using only the combinations of 4, 2, and 1 as a rule. Now we can rewrite 6 as 4 plus 2. We can rewrite 3 as 2 plus 1. Then once we rewrite this in the digits of 4, 2, and 1, then we put 1 as a multiplier if the digits 4, 2, or 1 is present. Otherwise, we put 0. So here, 4 and 2, we have to write now 4, 2, and 1 here as a complete. Then, because 6 is represented by 4 plus 2 only, so only the 4 and the 2 will be having a 1 as a multiplier. Then 1, which is not found in 6, then we just put 0 as a multiplier. Likewise for 3, because 3 is represented by 2 and 1 only, so you notice here that 4 will be multiplied by 0, and 2 and 1, which is now equivalent to 3, will be represented or multiplied by 1. Then all you have to do, class, is just look at the combinations of your ones and zeros. So here we have 1, 1, 0. Then the other one we have 0, 1, 1. Then we have to put together, combine them, okay, from left to right. Then of course the result will be the answer. So therefore 63 base 8, when converted into a binary, it will be 1, 1, 0, 0, 1, 1. Okay, so another example is 356 base 8 into a binary digit. So again, we are going to rewrite 3, 5, and 6 as a combinations using only the numerals 4, 2, and 1. So 3 can be rewritten as 2 plus 1, 5 can be rewritten as 4 plus 1, while 6 can be rewritten as 4 plus 2. Then once we were able now to represent them by the combinations of these 4, 2, 1 numerals, then we put 1 for those digits that has 4, 2, or 1, then 0 if it is not. Now, for the 3, because it's only represented by 2 and 1, so again, we put 1 as a multiplier, but we put 0 for 4 because 4 is not found in 2 plus 1. But for 5, we have 4 and 1 will be multiplied by 1, while 2 is missing, then we have to put 0. And for the 6, that is a combination of 4 and 2, so we have 4 and 2 will be multiply to 1, while your 1 here, which is not part of your 6, will be multiplied by 0. Then all you have to do is simply to get the combinations of zeros and 1s. So here we have 0, 1, 1, 1, 0, 1, then 1, 1, 0. But because here, class, we have 0 as the first digit from the left, then we just remove them. Then put together these three separated digits as one digit, and that will be our answer. So therefore, 356 base 8 is equivalent to 11010 base 2. So if we continue this one class, even if we have, let's say, another example of a 4-digit base 8 numbers, so 7125 base 8 will be converted again into a binary. So again, we have to rewrite our 4-digit 7125 into a combinations of 4, 2, and 1. So 7 can be rewritten as 4 plus 2 plus 1, so it's complete. 1 is 1, 2 is 2, then 5 will be 4 plus 1. Then the next step now is for us to put 1s to those digits, okay, if they are present. So 4, 2, and 1 for 7, so all the 3 are complete, so we have to put 1, all the 3. For the 1 here, so only 1 has 1, the rest have zeros. For the third digit 2, only 2 has 1, the rest are zeros. And for 5, we have 4 and 1 only with 1 as multiplier, then the others will be zeros. Then if you're going to uh, get now the ones and the zeros being multiplied to these digits, okay, then we are going to combine them or put them together. Then that will be the result class of 7125 base 8 when converted into a binary would be, of course, we have a 12-digit binary numbers here. So we have 111, 001, 010, and 101 in base 2. Now, if you're going to convert a hexadecimal number into a binary, so we just extend it, okay, by adding 8 as a combination. So a hexadecimal number class has digits from 0 to 9, including the first 5 letters, A, B, C, D, E. Of course, sorry, with the F, so we have the first 6 letters. So all in all, there will be 16 digits. So similar to base 8 or to octal, so we just use the 8421 as combinations. Then we put again 1 as a multiplier if the 8421 are present. Otherwise, we put 0 as a multiplier. Then the corresponding binary digits are the combinations of your 1s and 0s that are found beside each digits which are present. Okay, so here we have BE, base 16 into a binary. So remember class that in a hexadecimal, we have the first 6 letters from A to F as part of the digits. Now because BE are letters and this has an equivalent values of B has an equivalent value of 11 while E has an equivalent value of 15, so we have to rewrite them into numbers. So we rewrite the digit as a sum using only 8421. Then we know that B is 11, represented by 11, then E is 14. Then we rewrite 11 as a combinations of 8, 4, 2, and 1. So 11 can be rewritten as 8 plus 2 plus 1, while 14 can be rewritten as 8 plus 4 plus 2. Then we put 1 as a multiplier for these digits that are present, while 0 if the digits are not present. So 8 to 1 are present here, so you notice that 4 is not present in 11, so you have to put 0. While 8, 4, 2, these are present, but the 1 is not, so you have to put 0 as well, only 1. Anyway, if you're going to multiply any number by 0, class is always 0. And again, if you're going to multiply any number by 1 is the number itself. And if you're going to add, it will go back again to your respective values here. Then just remove or just concentrate on the combinations of ones and zeros. So this will be 1, 0, 1, 1. So we have 1, 0, 1, 1. Then the other one is 1110. So putting them together, it will be now 10111110 base 2. Okay. So the other example is 25A base 16 or 25A base 16 into a binary digits. So again, we have 3 digits here, so we have to rewrite them as the sum of 8, 4, 2, or 1 combinations. But we know that A is equivalent to 10, so we have to convert that into values. Then 2 is simply 2, while 5 can be rewritten as 4 plus 1, and 10 can be rewritten as 8 plus 2. Then we put 1s to the digits that are present in either in 8, 4, 2, or 1. Otherwise, we put zeros, which numbers or digits are not present. So for 2 here, only 2 is present, so we have to put 1. The rest will be zeros. Then for the digits 5, it's only represented by 4 and 1. So 4 and 1 will have 1 as a multiplier. Then the rest will be multiplied to 0. Then for A, that is your 10, represented by 8 and 2. So 8 and 2 will have 1 as multiplier, and the rest will be multiplied by zeros. So what we need, class, are simply the digits represented by the zeros and 1. So if you're going to uh, get them here, so we have 0, 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0. Now, because we have here 2 zeros, okay, on the left side, so you can just remove them. So it will be 1, 0, then the rest will be the same. Then we just put them together. Then the answer now of your 25A or 25A base 16 into binary digits will be 1001011010 base 10. So this is how we convert, class, or express an octagon, not an octagon, but an octal number or a hexadecimal number into a binary digits. Okay, so another example, we have to express D79 base 16 into a binary digit. So again, we have to convert or rewrite the D79 as a sum using only these 4 numerals. But D is a letter, class. In hexadecimal, this is equivalent to 12. So instead of D, we have to rewrite this as 12. Then combinations of 12 will be 8 plus 4 only, while 7 can be rewritten as 4 plus 2 plus 1, and 9 can be rewritten as 8 plus 1. Then the next step, class, is we multiply these digits that are present by 1, and those digits that are not present out of the 8, 4, 2, and 1 will be multiplied by zeros. So here we have the 8, 4, 2, and 1. So for the 12, it is only the 8 and 4 that are present. So we have 1s here, then the rest will be zeros. For 7, we have the 4, 2, and 1 are present. So we have multiplied by 1, but 8 is not, so it will be multiplied by 0. And for 9, it is represented by 8 and 1. So they will be multiplied by 1, then the others or the rest will be zeros. Then all we have to do is we are going to get these binary digits, combinations of 1 and 0. So we have here 1, 1, 0, 0. We have here 0, 1, 1, 1. Then we have 1, 0, 0, 1. So put them all together, and that will be now the answer to the D7916 as the binary results. So it will be now D79 base 16 is the same as 110001111001 base 2. Okay, so hopefully, class, you were able now to have an idea on how we are going to convert an octal number or a hexadecimal number back into a binary digit. Thank you, class, and see you again for the next presentation.